Hi, my name is Tara Paglino. I chose to do my final project on predicting clonal hematopoiesis. Real quick, clonal hematopoiesis is a condition in which somatic mutations occur in hematopoietic stem cells due to the process of normal aging. These now genetically distinct cells give rise to an entire population that can lead to certain types of cancers and blood disorders. I chose my data set from Data Mendeley. You can see the link there. This data contains clinical and mutation data for 5,649 patients with and without clonal hematopoiesis. And the aim of this project is to set up a model that can accurately predict whether a patient has clonal hematopoiesis or not based on the variables within the data set. So I'm going to go through prepping the data here. There are a few little things that made the data a little bit messy, so I went ahead and cleaned them up, whether there was an asterisk or a space in some parts of the data. And then I also showed the package I used for creating dummy variables. And then I went into exploring the data. So anyone can get clonal hematopoiesis, but it's typically age onset, so you see it most in individuals that are 65 and older. I went in because they have a bunch of tumor data to see, like, is there big differences in individuals that have clonal hematopoiesis and don't have clonal hematopoiesis? And honestly, I didn't find like a huge, completely different cancers. So, like, maybe these will have some pull on our features, but that we set up for the model, but I'm not going to spend too much time worrying about this. Lastly, the most important thing or interesting thing that I found was that everyone with clonal hematopoiesis has at least one of the genes mutated, these 5 genes. So DA5030 has the highest frequency of mutations amongst the patients with clonal hematopoiesis. So I'm going to go ahead and start running my code. So here we are loading the packages for the entire project. I'm going to go ahead and just load in the CSV and not spend too much time going over the data because I just went over that in the slides. Here I'm just cleaning up the data as I explained and creating the fast dummies creating the dummy variables using fast dummies package. Here I'm just running code for all of the figures I showed you on the slides. So we're going to go ahead and run some correlation and the correlation plots. Basically what I found here is that mutant gene expression in CH positive patients both seem to be slightly elevated in age. And we can see that down here. They all kind of have upward trends when looking at age. And I, again, ran some correlation plots on the clinical data, and we find that there are some outliers. So I'm going to go ahead and detect and remove those outliers. So when I remove the outliers, again, we see that the data is a little bit more clean. So I'm going to go ahead and impute this data now. The only missing data was amongst the clinical data, so I'm just using things like white blood cell counts, platelet counts, those kind of features to impute all of the missing data here. I didn't want to pull it out because it is a large chunk and maybe those features won't even be important, so we don't want to lose all of the genetic data as well. Here I'm just going to normalize the data based on this function that's built here, the min-max normalization function. Here I get into the feature selection. So I do a principal component analysis and a stepwise backward elimination to remove all of the non-significant variables. So looking at the scree plot from the principal component analysis, we see there's about 5 or 6 components that make up most of the variability of the entire data set. I'm going to go ahead and tell you that those are the genes and age. And I also ran the AIC backward elimination to see what kind of features that also pulled out. So I also have the formula here, which we will be seeing in a few minutes. So I'm going to go ahead and split my data into train and test set. I used 75% of the data to train on and 25% to test on because I wanted as much data as possible to train on because we are trying to diagnose patients. So we want it as accurate as possible, and to do that we need more data. So I set up a support vector machine, and as you can see here, I have one built from all the variables from the AIC stepward backward elimination, and then one based on the principal component analysis. And I really kind of wanted to see how they stacked up together, if one was going to be more accurate or not. And actually what I found was the one from the backward elimination was more accurate by about, a few tenths of a point than the principal component analysis. So I actually just decided to move forward with all of the features found because it was more accurate. So I'm going to set up the rest of my models. So then I go ahead and run a logistic regression model just to see what is, is it everything's really significant? No, it's not. So when I go to tune the models, I'm going to pull those features out to see if I can get some better accuracy. And here we see, the logistic regression didn't do any better than the principal component analysis feature selection support vector machine. So, okay, let's see if we can do a little bit better and try it with a neural network model. And again, we see that the accuracy is still around 93%. So all of the models are kind of hovering around this 93% range, which isn't terrible, but I still kind of want to see if we can do better. But first, let's validate that this is true and not just a fluke that they're all just giving me these accuracies for no reason. And so I performed a 10-fold cross-validation. And okay, so the data I selected to do the cross-validation is 92% accuracy. So it confirms that these models are definitely working when we cross-validate. So let's go ahead and tune our models. I tuned the SMV by changing the kernel to polydot and removing all those features from the logistic regression that we found were insignificant. Again, the logistic regression was tuned by just removing the insignificant features and keeping only the significant ones. And then the neural network, I, again, used only significant. I added the hidden step of 5 in there, so we'll see how the accuracy turns out now. Okay, so I'm going to compare the accuracy of all the models now. And if we pop back over to my slides really quick, I've put them all in a chart, and we can kind of see that even the tuned versus the untuned, nothing really changes. Of course, for the neural network, the tuned, quote unquote, tuned doesn't do better, it does worse in accuracy. And then I also run a stacked ensemble model where it didn't improve. So the SMV model really is the most accurate. So continue just running the code in our stacked ensemble model to really just finish this up. And lastly, I just want to go over some conclusions that I had about my model. So using the significantly selected features, we can predict whether a patient has clonal hematopoiesis with around a 92% accuracy using a variety of different models to classify. Although 92% isn't horribly inaccurate, we are classifying for a medical diagnostic, so we need better accuracy when dealing with these kind of data and decisions. Lastly, I would just kind of suggest using more data to train and then classifying the cases as they arise to maybe better predict clonal hematopoiesis. That concludes my model presentation, and thank you.